14, we're going to talk about multiple regression. Now, coming to this chapter, in chapter 13, we talked about simple linear regression, where we had a single independent variable x. The objective in that chapter, simple regression, in that analysis, was to predict the value of dependent variable or response variable from the knowledge of the value or values of independent variable or explanatory variable x. What's different in multiple regression is simply the increase in number of independent variables. So oftentimes there are more than one factor, more variables responsible for the values or variations in the response variable, the dependent variable, that is the y value, the y variable. So our objective remains the same. We would like to be able to predict the value of response variable from several explanatory or independent variables. Now here's an important assumption we have going in this chapter, that there has to be some kind of a linear relationship between dependent variable and each of the independent variables. So assuming that, then we can actually come up with this deterministic multiple regression model. And our population regression model assumes that this is our population regression model right in here. So notice here we have x sub 1, x sub 2, sub 3, so on and so forth, up to k variables. Now the simple linear regression, if you recall, simple linear only had these two, correct? Just the first two terms in this polynomial expression. So now what we're doing is we're adding more betas to the model. So what are these betas? Well, beta sub 0, that would be the regression constant. That would be the y-intercept if all of the other values of the random variables assume a value of 0. And the other betas, beta 1, beta 2, and so on, up to base beta sub k, these are what we call the partial regression coefficients for first, second, third, and so on. So for example, beta 1 would be the partial regression coefficient for the first independent variable, that would be x sub 1. Beta 2 would be that of x sub 2, and so on. Now, when we say partial here, I have a paragraph for you. So what do we mean by partial coefficient? The word partial means portion of the total. So what that means in turn is that this would be a change in value of dependent variable for 1 unit change in the value of independent variable, assuming all other independent variables are held constant. So for example, beta sub 2 would be the change in dependent variable y due to x sub 2 if we kept all of the other effects, all of the other independent variables constant. So in other words, we want to look at these coefficients one at a time, keeping everything else constant. And by everything else, I mean keeping the values of other independent variables constant or fixed. Okay, so that's what I have in these notes 1, 2, and 3. So what are we going to look at, or what do we look for in a multiple regression output? You're already familiar with a simple linear regression output, so the multiple regression is going to look awful similar to it. It's just it has more independent variables. So these are the things that I have bulleted for you that we look for in a multiple regression output. First, we want to look at the regression equation. Then we look at the coefficient of determination. That would be the r squared. And something we didn't look at in simple linear regression, which we look at now, is what we call adjusted coefficient of determination. I'll explain what that is in a few moments. Next, we're going to look at the p-value. And the p-value here, we're referring to the p-value that comes from the ANOVA table. Now this p-value, we'll explain what these do individually in a few minutes. So this p-value actually looks at whether we have the correct regression model, the predictive model. And then we also look at individual p-values to determine whether the coefficients in the population model are 0, any of them, if any of them, or all of them. And of course, we look at for the standard error of estimate. Okay, so everything before, we have seen all of these in our simple linear model. It's just in the multiple regression model. We have this adjusted R squared, which we didn't really look at before, and also we did look at individual p-values. We just didn't look at so many of them, and we only looked at one, and that was for like beta sub 1, the coefficient on x sub 1. Okay, so let's take a look at an example, and it will be easier to illustrate these through an example. Okay, so in this example, it reads, so we have a data here that deals with the amount of prepaid card purchase at Starbucks. And I went ahead and centered the data for us to better observe the data. Okay, so here's what this data is about. This data shows the amount of prepaid card purchased at Starbucks. And we're going to use the customer's age, the number of days per month the customer makes a purchase at the Starbucks, and the number of cups of coffee the customer drinks per day. And finally, the customer's income. So we have 4 independent variables here, these 4. Okay, we have age, days, cups, and income. So here, the amount, of course, let's see, I have amount of prepaid card. That would be, instead of AMT, I use, it doesn't matter, PPD. There we go. Let me use PPD for prepaid amount, because that's what I'm using in my table. Then we have the age, the buyer's age. Days is how many days per month the customer makes a purchase, cups of coffee the person drinks per day, and income in thousands of dollars of that individual. So this is a data set with 25 observations. Now notice I have a highlight here. We do have a single purchaser or buyer of $200 prepaid card. So those do not happen too often, but it's not unlikely. But most of these are in the probably $20 to $50 range. Okay, all right, so whatever they are. And then we're going to, okay, let me actually, so what I'm going to show you is this, folks. I'm going to show you the regression output for this. So remember the objective. We want to be able to predict the average amount a purchase that is purchased by a person at Starbucks, the average amount of prepaid cards. That would be our response variable. Given the individual's age, again, how many days let's see, how many days per month they make a purchase, and how many cups of coffee they drink a day. All right, so what I'm doing here, and in the next few outputs, I'm going to show you actually Minitab outputs for these, because Minitab actually is richer as far as being an analysis software. It's much richer than Megastat. And then when I'm done, all said and done, we go and actually run this in Megastat. Ultimately, that's what you would like to be able to do. So here is the regression run for this data. Our regression equation, first of all, this is our regression equation. So the prepaid amount purchased is equal to negative 83.8. That would be, again, like the y-intercept, assuming age, days, cups, income is 0. And remember, the interpretation of that, it would be meaningless, negative $84 in this case. So, but it's just, it has to be there in order to make this regression model work appropriately. And we have 0.237 times age, 1.19 times days, plus 1.42 cups, plus 2.407 income. So notice how these coefficients are all positive. So that means age correlates positively with the amount of prepaid card. Okay, that is purchased. So does days, so does cups, so does income. So individually, these are all positively correlated with how much of a prepaid card is purchased. And all of these numbers that you see, negative 83.8, you also see them down here. So let me actually use my pen to highlight these. Okay, so I'm looking at these numbers. See, negative 83.8, negative 83.8. 1.19 times day, 1.19. So you see all of these numbers again in this format. Okay, so those are just repetitious. And then next to that you have SE coefficient. That means the standard error of the coefficient. So usually, again, for the constant, other than the coefficient, the constant, the y-intercept itself, we don't look at these other stuff. Okay, so don't worry about these. Okay, now look at the age. Age is 0.237, days 1.19, and so on. So let's take a look at, for example, cups. Remember, cups is how many cups of coffee that individual drinks per day. So the coefficient of cups is 1.42. The standard error of that is 2.63. That means, like, give or take 2.63 cups. And then here we're actually testing a hypothesis. That's one thing that's important here. We really do pay attention to these p-values. Okay, so I'm looking at over here now. Now these p-values, each of these p-values test a specific, very specific hypothesis. Okay, so let's take a look at, for instance, let's take a look at our first p-value here, other than this 0.001. Remember, we don't look at p-value for constant, but these are the variables in our model, independent variables. We do look at those p-values. So what is this 0.685 p-value looking at? So here, let me write this. Our null hypothesis that's being tested by that is that this would be beta 1. Okay, beta 1 is the coefficient on age, right? Beta 1 is 0. The alternative here says beta 1 is not 0. That's that simple. P-value for that is 0.685. That tests this hypothesis. Let's take a look at, for example, the last one, this one. So what is the null hypothesis for that? That says beta 4 is 0. That's the coefficient on the fourth variable is 0. The alternative here says beta 4 is different from 0. So in other words, what individual p-values are testing is that whether we need that independent variable in our model or not. Because if the coefficient is indeed 0, then let's say, for example, I have beta 1 times age. Okay, and if beta 1 is 0, if that's 0, 0 times age is 0. So that means you don't need age, right? Okay, so let's take a look at these p-values again closely. The first p-value is 0.685, which is a large p-value. So we do not reject the null hypothesis. Therefore, age as a predictor is not needed in this model. So I can actually cross that out. Next p-value, look at next one, 0.429. We don't reject that null either. That means you don't need days either. And what else? How many cups a day? That's not material. Notice every one of these p-values are large. So the null hypothesis, for example, for beta 2 is 0. We don't reject it, right? For beta 2 is 0, and we don't reject that one. So that means we don't need the second independent variable in our model. The only one that's really meaningful for us to keep is this one. It's income. Look at the p-value. P-value is almost 0. That means we have highly significant results. So we're going to reject this null hypothesis for beta 4 0. So beta 4 is not 0. If beta 4 is not 0, that means we need income in our model. Okay, so that's how we interpret these p-values. So it looks like as a predictor again, we don't need the first 3 variables. We only need the last one in our model. So you're going to see that I'm going to actually rerun this model with only income in just a few moments. Now, before we move away from this output, let's talk about what VIF is. The VIF stands for Variance Inflation Factor. Okay, and what the Variance Inflation Factor looks at, I'll get to this in a few minutes in this lecture, in this video, so I'll tell you more about it. But here, these are looking at a phenomenon called Multicore Linearity, which I'll explain and elaborate more about in a few minutes. So let me save that for it. So again, the takeaway from all of this, from this output, is that the ones that have high p-values, these variables we do not need in our model. There you go. The only one that we do need really is income in this model. Okay, so let's go further down. And next, what we're going to look at is, I'm right down here now. So the next piece of the output, we're going to look at 2 important pieces of information. One would be R squared, and the other one is S. Okay, the S here, that's the standard error of our estimate. Okay, that's what S is. S for standard error. That's what that is. Okay, now what does the standard error tell us? This would be like the give or take of your predictions at every level. So that's $22. That means any prediction we make, and we will make a prediction in a few minutes, any prediction we make at any level, we could be off by as much as $22, which is rather high, assuming again, or observing that these purchases are all in the range of mostly $5 to $50. So if I say, well, the next person walking in, if that person is an average person, is going to purchase $60, I could be off by as much as $22 on that, give or take $22. Okay, now the next important idea here is R squared. Now, we talked about R squared before in simple linear regression. Remember, R squared told us how adequate or how useful our regression model is. We're going to use the same guide as before. We prefer to have R squares that are in the order of like 90% or more. 70 to 90 is adequate, so this is okay model for prediction. R squared is 75.46, so that means 75% of variations in the price of those prepaid purchases is explained by presence of age, days, cups, and income. Those 4 variables combined and collectively explain for 75% of variation in the amount of prepaid cards purchased. And that would be again on the for the average amount that's purchased. Okay. Now, something that we ignored in simple linear regression, which we do not in multiple regression, is the adjusted R squared. This adjusted R squared, notice, is actually less than just ordinary R squared. Okay, so what is this adjusted R squared? The adjustment that's made here is for the number of independent variables that are in the model. Okay, so that's what that is. That's called the adjusted R squared. We make adjustment for how many variables are in the model. So the more you have, the more independent variables in the model, the lower the adjusted R squared gets. In fact, it actually penalizes you, this thing. The adjusted R squared actually penalizes you for having too many independent variables in your model. Its interpretation is exactly the same as before. So we would like to have high adjusted R squareds, 90% or higher. Okay, and don't worry about R squared adjusted for predictions. That's if you like fit the model using the model, your R squared for the model is actually going to be that. So don't worry about this one. Okay. Now, let's continue on. So for this one, again, this is the ANOVA now. This is the analysis of variance for the full model. The full model has all 4 independent variables in it. You see that? Age, days, cups, income. Okay. So, our sources of variability are regression and error. And Minitab actually breaks it down by independent variables. Again, don't worry about these individual numbers. One thing that you will note is interesting is you see this like 0.685 goes back up here. 0.429, these are all repeated in here also. You see that? So their interpretation is exactly the same. So you could actually get these individually as p-values in the individual coefficients tableau, or you can actually get it in the ANOVA output. Now, one thing that is important, and we'll get to that also, is this p-value now. This p-value for the regression model. Okay, so that p-value is testing the overall fit of the regression model. Okay, so what is the null hypothesis here? The null hypothesis here is that beta 1, beta 2, beta 3, and in this case, because we have 4 independent variables, we have those subscripts. These are all 0. Notice all of the betas are zeros, whereas up here we looked at individually those betas being 0. So here we're looking at the collective betas being 0. And clearly this is significant, right? P-value of 0. The alternative here, what does the alternative say? The alternative says that not all betas are 0. At least one of them is not 0. Okay, so that's what that is. And because p-values is small, we're going to reject this null hypothesis. Okay, so we're gonna reject the null and side with the alternative. That means, yeah, this is a good predictive model for what we want to do. Okay, and this is what we call the global test of hypothesis. That's what that global hypothesis test is. Okay, now let's continue on to the next piece. Let me see. This part again, Megastat doesn't give you the output in this form. We'll see the Megastat output in a moment, but the reason I'm doing it using Minitab is because Minitab gives you much better output with more information. It's more complete. Okay, so here is diagnostics for unusual observations. That's what we're looking at. So it found one unusual observation. Remember that $200 prepaid card? The fit means predicted value here. The predicted value with those conditions. Let's say go back to $100 one. This one, observation 15. An individual with these characteristics. Okay, what are the characteristics? If a 40-year-old person, an average 40-year-old, who on average goes to Starbucks 15 days a month and drinks 5 cups of coffee a day, not necessarily at a Starbucks, whose income is $80,000 per year, is expected on average to purchase a $200 card. Well, this is the actual. How much is the average person with these characteristics expected to purchase is $143, not $200. Okay, and then next to that you have the residual, which means the error, right? That's the difference between $200 and $143. And then the standardized residual. So that's what this is. Okay. Again, Megastat doesn't give you that, but that's interesting information. And here R, what's the significance of R? R means large residual. So the standardized residual is 3.57. Okay. We would like for that standardized residual to be much smaller, near zero, preferably near zero. And this is 3.57, so that's rather large. Okay, so there you go. This is really a regression output. That's what we look at. That's what we really want out of our regression outputs. Now, because the fact that we have so many independent variables in our model, there is potentially a possibility that we have duplicate independent variables that give us duplicate information. Okay, so anytime we have multiple regression model, we should concern ourselves with the issue of multicore linearity. Multicore linearity is when independent variables become correlated, and that's what's called multicore linearity, because it's relationship in a multiple regression model. Because we have multiple independent variables, and we're looking at correlation, linear correlation between them. So that's what it's called, multicore linearity. Okay. So how do we safeguard against multicore linearity? Don't remember, the more independent variables you throw in your model, the more likelihood that you create multicore linearity issue. So one thing that the output helps us with, that gives us one measure of actually diagnosing for multicore linearity, it's VIF, or variance inflation factor. That's what this is, variance inflation factor. Okay, so with variance inflation factor, that means how much of the variance is increased if your predictors are correlated. Okay, so if these factors, if these variables are not correlated, then we would expect the VIF, variance inflation factor, to be about 1. Okay, so the magic number here is 10. If you have VIF greater than 10, then you can actually call that variable that has a large VIF, call it that is there is multicore linearity between that variable and the other variables. Okay, so let me go back up here and look at VIF in this exercise. So these variables are not correlated. Okay, I mean, there is some correlation, but it's just basic correlation. As long as the correlation between any two independent variable is between -0.7 and 0.7, then there's no issue with multicore linearity. Okay, we can actually look at the correlation matrix on this one, and we'll investigate this. And we'll do that in Megastat. Megastat will give us the correlation matrix, and we can see if these variables are highly correlated or not. According to VIF, they're not. So in other words, I would expect when we do a correlation matrix to see correlation between independent variables that range between -0.7 and 0.7. Okay, so there you have it. No issue with multicore linearity. And by the way, what do you do if the two variables are correlated? Well, you've got to remove one of them. Okay, and that's the remedial action, is to remove one of them. Because remember, that means if there's high correlation between them, that means they're not really giving you any more information about the dependent variable when they're both in the model. One of them is good enough. You don't need both of them in the model. Okay, so here's again our regression equation for this problem that we just looked at. And I want to make a prediction here. Well, I want to predict the average amount of prepaid card that's going to be purchased by someone who's 35 years of age, visits the Starbucks 12 times in a month, that's quite a bit, and drinks 3 cups of coffee per day, and has annual income of $50,000 a year. Now, just because they visit Starbucks, let's say 12 times a month, doesn't mean they're going to buy the prepaid card, right? Sometimes they may use their cash. Sometimes they may just sort of go along with their friends. Maybe somebody invite them for a cup of coffee or something. So, but whatever it might be. And so here's what I did. I actually put in the information, 35 years of age, and then they visit the Starbucks 12 times a month, and they drink 3 cups of coffee a day. Again, they don't drink all 3 cups necessarily at the Starbucks. They could go to Starbucks just to study, right? Just take their the computer and study with their friends. So they don't necessarily purchase coffee. Or they could go in buy something other than coffee. Okay, and there you have it. So, and the person's income $50,000. So I just plug those numbers into our regression model, which is this model. And I got the expected value of $64. So we expect that individual with these traits to spend about $64 at Starbucks purchasing a prepaid card. Okay, that's not spending $64. That's if they're going to purchase a card, that's what it's going to be. Okay, and of course, right in here, you're going to see actually, right in here is our predictions using those numbers. So the software did the same thing. It plugs in the numbers, gives you a fit. The fitted number is the expected value of dependent variable for those individual values. Okay, that is for 35 years of age, 12, 3, and so on, and that one. Okay, so given these, again, characteristics, you expect $64 purchase. And of course, the standard error of the fitted value is this one, and 95. This value, standard error fit, is used to construct confidence interval for the prediction at that level. Okay, that's what that is. Now remember, at every point, our predictions could be off by as much as $22, right? So the $60 could be off by as much as $22. Okay, and again, I'm just recalling here the things that we look in a multiple regression output is, let's see if we look at these for now with this example. We looked at the regression equation. We talked about the coefficient of determination. We looked at adjusted coefficient of determination. In a multiple regression model, by the way, you really look at this as opposed to this one. This is more important of the two, the adjusted coefficient of determination. Because remember, just by nature, you can throw in unrelated independent variables in your model, and that will boost the R squared. That's just the nature of regression model. You can put the sales of chewing gum in your regression model, and it will improve the predictability of your model. But whether it makes sense or not is another thing. Also, we looked at the first three. We need to look at the p-value for the overall fit. Remember, that's the global test of hypothesis. We looked at that. So that was a good predictive model. We looked at individual models, individual p-values, and we decided that only income was significant. And the standard error of estimate we talked about, that was the $22 that I talked about. So, and the R squared being this high, again, what I'm doing is I'm just going to make sure I cover these again. We already looked at some of these before, so this is redundant. And here is our p-value. So remember, the p-value from ANOVA actually is testing whether you have the correct model or not. Okay, do I have the correct predictive model? Looks like we do with this one. We do. Now, whether we need some of these independent variables or not is another story. So again, for this example, because p-value from the regression is almost 0, we're going to reject the null. And rejecting the null means alternative, which is this one. The model is actually a correct model for predictions. Okay. Now, some people look at the f value also. This is like the f test. The f value leads to p value. But remember, I don't show you the formulas here because we use the software. So we use the f test. We use the f test for the global hypothesis test for the fit of the model. We use the f test, which leads to the p-value in the ANOVA. Keep that in mind. We use f test to test the global hypothesis for the fit of the regression model. Okay. And here I have again symbolically written what I had written earlier. It's just in print. Now, we're about to look at what we looked at earlier. Remember those individual p-values? So that would be the answer to this question I have. Do we need all the predictors in this model? Okay. If not, which ones are either redundant or not necessary? And by that we mean they have no predictive power by themselves. So again, recalling something we've seen earlier, remember the high p-values, we do not need them. And we're using 0.5, we're using alpha 0.5 as our guide here. Anything larger than 0.5 we discard. So you don't need age, days, or cups. You only need income to make a good prediction. Now, if we actually throw away these 3 independent variables, age, days, and cup, that's going to improve our adjusted R-squared. And usually what happens is we run the analysis with and without these independent variables and take a look at R-squared and adjusted R-squared. Okay. So the leading predictor again in this example is income. Okay. Now, here's what I'm doing. I'm running a new model with only income. And there you go. So for this one, we're looking at this model that y hat is equal to beta 0 plus beta 1 x1. And x1, well, let's just call it income. Okay, let me do this, just put the words to it. Okay, so I'm doing beta 1 times income. That's what I'm assuming my model is. Okay. And look at the R-squared and adjusted R-squared. Also, look at the standard error of estimate. Remember before we could be off by as much as $22? Look at that. Now we could be off by almost the same amount. So that really didn't change it much. And we managed to get rid of 3 independent variables. That's not bad. Now, why do we like that? Is because, you know, keeping track of those independent variables, we rather not have them than have them in the model. Okay, so our model is also an easier model to work with. And look at the adjusted R-squared. Adjusted R-squared is 75. And look at R-squared, again, how close they are. At this point, with just one predictor, we are back to a simple linear regression model. You see that? And when you only have one predictor in the model, adjusted R-squared doesn't matter anymore. And notice how close they are anyway together, 72 versus 71. So with just one predictor, you only look at R-squared, not adjusted R-squared anymore. Because there is no other variable, independent variable to throw away. If I throw away income, I have no predictor in my model. Okay, and there you go. Look at the F test. in the ANOVA. Our p-value is 0, and just like before, that means we have a good predictive model. And what I did is I actually now want to predict the amount of prepaid card that's going to be purchased by the average person, the person who makes only $50,000 a year. See up here, remember when I made a prediction? I used 50,000 with these other information. So we don't want this other information now. We're just going to say, well, let's just keep 50,000 a year. And remember, our prediction was $64, right? The average person with that income purchases a prepaid card that's worth $64. Let's see how much that amount's going to be now. With just income, it's going to be $65.64. Notice it didn't change much, right? It was $4, right? Yeah, $64 up here. It was $64 versus almost call it $66 now. 65, 64, not much of a difference. And this is our regression model that you see in here. That's our regression model. Okay. And let's see. In here, I'm trying to see age, days, cups. Okay. And what I've done here is actually, I see what I did here. Now, income, again, was the most significant predictor, right, for this regression model. So what I did actually is I took income out and I put the other three in there, age, days, and cups. With age, days, and cups, remember the most relevant information, the most important, was income. So with just age, days, and cups, look at our R squared and look at adjusted R squared, how poor that is. 9% of variation in the amount of prepaid cards purchased at Starbucks is explained by age, days, and cups. So those are not good predictors for purchase. And our standard error is now almost $40, used to be $22. So just again, I'm just playing around with this, looking at it from different angles. This just reinforces the fact that we do not need age, days, and cups for our predictions. And look at actually now a negative coefficient on cups. So in presence of age and days, the more they drink and the more number of cups, right, they drink per day, actually the purchase goes down. So I'm not sure if that's good information, but and this is important. Check this out. Remember, this is the p-value from ANOVA. The p-value from ANOVA looks at all variables that are in that model. Okay. So for this one, the p-value is 0.176, which is large. So we do not reject the null. Now, we do not reject the null. And what is the null? The null says beta 1, beta 2, beta 3. Those three independent variables are 0. Okay, and that's what that shows. So again, it just reinforces what we found out earlier, that we don't need these predictors, right? And this one tells us with those three in the model, you don't have a good predictive model. You don't need any of them. Those are not the right model. Or this was not the right model. Okay. So again, the full model, what I call the full model has all of your independent variables in it. And then you have reduced model. The reduced model is when you start to throw away independent variables. Okay. So here, I'm trying to give the interpretation of the coefficients. Now, this is important. How do we interpret the coefficients that are on the predictor variables? So let's take a look at this one. The coefficient is 0.237, means 23 23.7 cents, $0.237, 23 cents, almost 24 cents, 23.7 cents. What that means is the change in prepaid. So prepaid dollars over age. Okay, I'm going to write 0.237 as 0.237 over 1, which means 23.7 cents per 1 year, right? So that means for each additional increase 1 year in age of the purchaser, you expect the purchase amount to go up by almost 24 cents. Okay, and that's what that is. And this is actually what the partial, this is the partial coefficient is. This assumes all of the other variables, days, cups, and income are held constant. Okay, so assuming we keep all of those constant, then the partial coefficient is 23.7 cents per year. And I have it here again, holding other three variables constant. Okay, so that would be the interpretation. Let me leave this one under for you. Okay, this was age. Okay, and what about the coefficient on days? This one now. What does that mean? Well, same thing. That's 1 unit increase in days per 1 day increase. It's gonna be $19. That's the change in the amount of prepaid card purchase. For each additional days that they visit Starbucks, you expect them to spend $19 more. So if they go 2 days, that would be $2 and almost 40 cents. 10 days, it would be almost $12. That's just assuming everything else is held constant. That means age, cups, and income are now held constant, and so on and so forth. Okay, so let's now take a look at Megastat Output. Hopefully this will look familiar to you, and then we actually go to Megastat. I'll show you how to run this on Megastat. So with our Megastat regression output, look at this. I did a copy-paste job. And all of the numbers are the same, so I'll go quickly over these. Here's R squared, and here's adjusted R squared. We've seen both of those. Okay, and N is the sample size, K is the number of variables, the standard error of estimation, $22 for every prediction. Okay, and then we have the ANOVA table. The ANOVA table, our p-value, remember in Minitab it gave us 0 like that, right? So it's 6.7 times 10 to negative 6 power. That means 1, 2, 3, 4, 5, and then 6, 7, 6. That's how small the p-value is. Rounded to nearest 10 thousandths is a 0. So very small p-value. So we definitely have a good predictive model. Remember, this p-value looks at or tests at the global hypothesis test that all the coefficients are 0. Means you don't need any of these independent variables. You have totally the wrong model, totally. Our regression output, right in here, are variables. Age, days, cups, income. I have them in yellow. Income is p-value is highly significant. The others are not. So we can do away with the other three, but not income. We definitely need income in our model. And then here's our confidence interval for each of these coefficients. So for example, when we say for each additional year increase in age, you expect about 24 cents additional purchase on the card on average. Okay, so when we look at that one, a 95% confidence interval on that, it could be anywhere between -$1 to $1.50. Of course, -$1 doesn't make sense, but that's just the theoretical number. Anything that's negative, you can safely go from like 0 to that amount, to the upper limit. Look at income. The income coefficient is 2.4. That means for each additional increase in income, 1 unit increase in income means another, what, $1,000 per year. The person is on average going to purchase $2.40 more on the card. And that number could range anywhere from $1.65 to $3. Okay, that's what these in standard errors look at, the standard of individual variables. That's not the same as the standard error that we saw up here. This standard error, I'm up here. See that? That standard error and this standard error are different. These are for individual variables. This is for all of them collectively. Okay. And look at the variance inflation factor. Megastat gives you the average variance inflation factor. Also, again, each software is programmed to do different things. So there's no issue with multicore linearity in this problem at all. And I went ahead and made one prediction earlier. Remember, $64 for individuals that had these characteristics. We expect that person to purchase on average $64 in prepaid card from Starbucks. The lower prediction confidence interval, the lower limit is $47, anywhere from $47 to $80. And then 95% prediction interval is $14 to $112. Okay, to $112. And the difference between them, remember, confidence interval, we establish it for the average value. The prediction interval is for an individual observation. So here's the interpretation how these are different. For 46, or let's call this $47 to $80, we expect on average, individual with the average person with age 35, average number of days, average number of cups, average income of that. Okay, or just with those characteristics, on average they make a purchase of $63. Anywhere on average, it could range from $47 to $80 their purchase. This is for the average purchase. Okay, now you might want to say, okay, well, let's say I'm sitting in Starbucks. An individual walks in which meets exactly these criterions. One person walks in. Okay, a single individual walks in. This person is 35 years old. He or she visits Starbucks 12 days a month, drinks 3 cups of coffee, and has income of $50. I would expect that one person, not the average person with these characteristics. We could have thousands of people that fit this description. The $64 is the average purchase for those many individuals that fit the bill here. But the one person that walks into a Starbucks that fits these characteristics, you expect him or her to make a purchase anywhere between $14 and $112. So again, on one we use the word average and the other we don't. For confidence interval, we use average. Okay, for this one, we use the average. For this one is for an individual. Okay. All right, so we're good with this. Now we're going to go to now Megastat and actually run this in Megastat. But as far as the OneNote, oh, okay, I see. I almost left this out. Now this is not in your book, by the way, but because it's in the Megastat output, so I thought I'd talk about it Megastat also give you this thing called leverage, 0.129. We would like to have a small leverages near 0. So this is perfect. So what is a leverage? A leverage tells you pretty much how far the independent variable values for an observation are from the remaining observations. So if you have high leverage points, means this observation is far away from everybody else. And so for example, in the case of simple linear regression, you have individuals here, and then I have one that's over here. Remember, we call these influential observations. So this one individual here is going to have high leverage. That means it's farther away from the rest of the data points. So this again, this single individual with these characteristics, this is a single data point, has a leverage of 0.129. So that means it's not too far from the rest of the group. And that's one way to assess influential observations and decide if observation is influential or not. Okay, let's go to Megastat. And in Megastat, actually, I'm going to do a correlation matrix here, and then I'm going to copy paste it down here below leverage to finish this work. So let me go to Megastat now. Okay, so here we are in Megastat. Now, same data as you saw in my note. I went ahead and actually typed in the values that I need in order to make my prediction. Okay. So let's go. I actually run our multiple regression output now. So you click on add-ins, Megastat, and we're going to go down to correlation and regression. You don't want to do scatter plots. Scatter plots are for dependent and one independent variable. We have multiple. If you want, you can actually do pairwise. You can look at dependent variable and each of the individual independent variables if that's what you want. I'm not going to run that. Let's take a look at actually, here's a correlation matrix. Let's do that because I haven't done that. So the correlation matrix, our input, expects a matrix here. So I'm actually going to, hopefully this works. There you go. I'm actually going to highlight all 5 independent five variables. First one is dependent, the other 4 are independent variables, and hit enter. And there's really nothing else there that I need to input. Just hit OK, and there you go. So here's our correlation matrix. Now the correlation, the ones that you see ones along the main diagonal, that's always the case. Because, for example, age correlates with itself 100%. Income correlates with itself 100%. So we do not look at these. Okay, so I'm just gonna, and there you go, highlight these maybe in gold. So we don't look at those. Okay, now we're interested in looking at, if you want, you can actually look at the correlation between dependent variable now, prepaid amount, and each of these individual variables, independent variables. So prepaid, look at prepaid correlates the greatest with income, 0.85 correlation. That number, we like it to be high. That we like to be high. Okay. So the correlation of each of these with dependent variable, we would like these to be high. The correlation between independent variables, we don't want those to be high. Okay. So let's see. And this one, for example, the correlation between age and income is 0.178. Now I'm going to highlight these in a different color. Okay, let me color these in maybe blue, light blue. Okay, and of course this matrix is symmetric. I'll explain what I mean in a moment. So there you go. Here we're looking at everything that's in blue. Look at the correlation between independent variables. So days and age, correlation 0.37, not high. That's good. Remember, we do not want high correlations in the blue. These correlation must be between negative 0.7 and 0.7. If that's the case, means there is no multicore linearity. So none of these are high. In fact, that's good. So they don't correlate with one another, with each other. So we don't have any problem with multicore linearity. The greatest correlation is almost 0.6, and that's days and cups. Now, the reason this upper triangular formation is blank is because the correlation, for example, between cups and days is the same as days and cups. So if you wanted to, days and cups would be here. If you want, I can type 0.588 here. You see that the number that's in here, 0.588, and I don't know why it's not staying, but it's there. You can see up here, maybe because it's painted. Let me go no fill in this one. There's something here that the output has done. You go automatic 0.588. Anyway, so you don't need these numbers anyway up here. They're just mirror image of the numbers that are below the diagonal. So that's what this correlation matrix is good for. Okay, now here is testing a hypothesis. This is testing a hypothesis that there is a correlation between, let's say, income and prepaid. So you can ignore those. But that's what the correlation matrix is. Now let's actually run the regression, Megastat regression analysis. So our independent variables here, x, it's going to be age, days, cups, and income all the way down, right? Make sure you highlight all of the observations. These are our independent variables. Our dependent variables, that would be y. Dependent variable is prepaid amount, highlighted. And here we actually want to type in predictor values. Remember our predictor values were 35, 12, 3. You got to put them in the order of your model. Our model was age, days, cups, income. So I'm typing in my age, days, cups, income of 50. Oops, that was comma 50. Don't type 50,000. The income is in thousands. And in here, see variance inflation factor. You can click on that. I'm going to uncheck test for intercept. We don't usually test for intercept. And for this course, that's all we want. Hit OK. Oops. Define object error. Oh, I don't know why it gives me the error, but it's going to give me the output anyhow. Okay, so there you go. And that's the regression output. We already went over the output, so I'm not just going to go over the output again. But that's how you get it in, in Megastat. But the correlation matrix, that matrix, I like it. I'm just going to copy and paste it into my note. Okay. And let me pause the video while I do that. And there it is. Here's my correlation matrix again. And I just copy and pasted it into my my note, and there you go. So that's gonna wrap up the discussion of multiple regression analysis. And again, there is a whole lot more to this. We're just giving you enough information so you can use it if you have to at this level. And with that, we are done with this lecture.